Good afternoon, everyone. Welcome. It's great to have you here for this webinar that we're hosting today called Intermodal Data, a practical introduction to understanding its full potential. I'm really excited because I think data's been on everybody's mind. We've had a lot of requests for doing something on data, and I'm really pleased to bring some experts to shed some light on the opportunities that it presents to us. I'd like to thank our sponsor today, BlackBerry Radar. They were kind enough to help sponsor our Business Intelligence Services series, the second in that series, and a really important one. Data's been important for years, but I think it's really kind of coming into its own as an operational tool that people are really starting to want to dive into. I'm excited to be able to bring to bear two experts from one of our member companies, Inform Software, which is based in Aachen, Germany, but has operations around the world. And Alex and Matthew will tell you a little bit more about that. But I'm really pleased to bring Alex Van Winkle, who's a senior consultant with Inform Software, and Matthew Wittermeyer, who's the marketing manager. And they're going to take us through what I think is going to be a really compelling presentation, both in terms of what they teach us, but also the opportunities that they open up for us, I think. So without further ado, I am going to turn it over to Matthew to get us started.
Hey, thanks, Hal. I'm just going to back up one slide. Before we take into the educational component of today's webinar, I think it's important for you guys to learn a little bit about Alex and myself, and to get a really brief overview of who Inform is and why we're qualified to talk to you today about data and its application value. And for us, that means artificial intelligence and machine learning. So as Hal noted, the first voice on the call, I'm Matthew Wittermeyer. I'm the marketing manager for Inform's logistics division with a special focus in container and intermodal terminal operations, as well as post and parcel operations. I've been with the company now for 4 years, and in that time, I look after a lot of the content writing, conference presentations, and contributing a lot of that content into many industry publications. I'll let Alex introduce himself. He's the second voice on the call.
Hi everybody, my name is Alex Van Winkle. I'm a senior consultant for Inform. I've been with Inform for 11 years now, and I've been mainly involved in container terminal optimization project, as well as projects within the postal and parcel realm we do at Inform. And as you can hear, I'm the one with the strange German accent.
So Inform as a company was established in 1969 when Professor Zimmermann, who was lecturing at the RWTH University here, decided that he wanted to prove that this field of computer science, or mathematical science that he was working in, called operations research, could in fact be applied to improve business decision logic. And they say the proof is in the pudding. Long story very short, we celebrated 50 years as a company last year, and we've grown quite substantially over that time. Since 1985, we've sort of started to commercialize products and expand our market reach. And I think what's quite interesting about Inform is that we're entirely internally owned. So we're not really tied to external stakeholders or necessarily a pure sort of profit-driven approach, which allows us a huge degree of lateral thinking, where we're allowed to explore new ideas and come up with clever new ways of approaching the markets that we work in. Hal rightly pointed out that Inform is based in Aachen, Germany, and we've got regional offices in the United States, in Atlanta, and we just recently opened up an office in Sydney, Australia, which allows us to serve our global customer base of over 1,000 customers, many of which are Fortune 500 companies, for quite a sustained period of time. We really value long-term relationships with our customers above and beyond, again, those short-term profit opportunities. And that's sort of proof in the pudding. Again, some of our oldest customers have been with us north of 35 years. Our oldest container terminal customer is Hamburg Port, which is Hala there, who this year celebrates 20 years. Inform as a company is 850 people spread across 7 business divisions and a centralized R&D operation. The R&D operation works for all of the various business divisions, and that allows us to leverage insights and learnings from other peripheral industries. A lot of the machine learning applications that we started to introduce into the container and intermodal markets in 2018 were actually first tested and refined in, for instance, our risk and fraud division, where we're detecting fraudulent transactions for major banks around the world and major credit card holders. So we get to learn from a lot of other people's mistakes whilst putting together what we do in the terminal market. Speaking of the terminal market, we're very blessed as a company to have a prestigious lineup of customers. You see, for instance, up there, APM Terminals, Hala, which again is the Hamburg port, and Port of Rotterdam are some of our larger customers. In the North American market, you guys will all be familiar with, I'm sure, TraPac and GCT, where we're doing a lot of rail operation in their Vancouver facility. And from an intermodal perspective, we've got a very large footprint here in Germany at home. And of course, we're always looking to expand our intermodal offering in the North American market. That's enough about us. Alex is going to take over for a little bit and sort of start to touch on what artificial intelligence is and the relationship to data.
Exactly. So let's see what we actually want to tackle during today's webinar. So we want to learn about general artificial intelligence. So we want to learn about systems that know intelligent behavior and mimic human behavior. And we get used to it in our daily lives, and we see it every day. So for example, when we enter our car and push a button and tell the car where it has to guide us to, then the car understands our input and delivers an output, which then would be the route that best fits to the criteria we preset. Another example would be our favorite online store, which makes such nice proposals for our next buy, for our groceries and so on. And that leads us to a special kind of AI, which is machine learning. Basically, machine learning is using algorithms to bit by bit learning from the past behavior and deriving models to adapt data accordingly. So it makes predictions about the future. It is not projecting the past behavior into the future, but continuously learning. And then what spices the soup is to use AI and or machine learning complementary to operations research. When applying optimization algorithms, we take into account certain input data to calculate an optimized outcome. In a traditional way, this input is part of either the base data or it comes via an interface. When combining OR and machine learning, however, one can squeeze the most out of the optimization or out of OR models just because of the better input data. And you could also split or also flip that coin and just see it from another angle. So when you develop a model in machine learning to detect a certain outcome, you're naturally facing optimization tasks, which you solve with operations research. So to sum it up, in the course of the webinar today, we're going to learn more about artificial intelligence, different machine learning methodologies, and Matthew and I are going to present to you how a machine learning project can be started by giving you a very practical and abstract example. And then in the last bits, we are going to explain to you where and how we've already applied machine learning within the container terminal world.
Thanks, Alex. You've certainly scratched the surface on what artificial intelligence is, but we want to take a little bit of a deeper dive. So looking at it, artificial intelligence has been around for the better part of the last century. Although it's been recent advances in both computer hardware and algorithms that combine to have given it the kick that we've seen in the better part of the last decade. The other major advent that's changed in the last decade and a half is the invent of big data. So one of the early challenges of artificial intelligence was that there simply wasn't enough data available for these computing systems to progress. Because it's progressed a lot over the last 20, 30 years, there's actually quite a few sub-branches of artificial intelligence. Most of us will have a smartphone in our pocket, and they all come equipped with a digital voice assistant. I'm carrying an iPhone, and so it's very common for me to say, "Hey Siri," and ask her something. That's actually artificial intelligence that's first utilizing the red circle, the perceiving and acting. When you send a command to Siri for her to do something, she's utilizing a natural language processing algorithm to detect what it is that you've said. Then she moves into the teal circles of problem solving to try and understand what it is you've asked her. And once she's understood your command, she moves into those green areas where she's starting to use her knowledge database and some fuzzy logic to generate a response or some sort of an action that you've requested. More recently, in the last sort of 5 years, we've certainly seen an uptick in the hype around machine learning, and it's the area where we're going to focus in as we progress through this webinar. But more to the point that Alex started in the previous slides, from a purely scientific perspective, artificial intelligence and operation research are two distinct branches of science. However, in the last 20, 30 years with the advent of computing, again, they've both evolved towards a common end goal, which is using advanced computer systems to mimic intelligent decision making. And in that regard, there's two areas where they overlap very strongly. The first is in that forward thinking, anticipating the future, which is problem solving, where OR has always traditionally focused. But certainly more recently, as Alex noted, we found that by better understanding the past, we can take more informed decisions about the future, which of course then segues nicely into our second major question for the webinar. What is machine learning? Alex?
Yep. Yeah, so basically we categorize machine learning into 3 sections, into supervised machine learning, unsupervised machine learning, and reinforcement. So let's start with supervised machine learning. Supervised machine learning allows you to collect data or produce data output from previous experience. So within supervised machine learning, the regression technique is quite a popular one. It predicts a single output value using training data. It helps you to optimize performance criteria using experience. So
the example that we're seeing here, of course, is looking at past weather data. Admittedly, it's in German, but it's looking at past weather data to assist in predicting what the likely weather is going to be on your extended forecast. So it will help you and helps meteorologists answer questions like, do we need an umbrella for the upcoming weekend, or is it going to be like last weekend here in Germany where it was absolutely beautiful and we had the barbecues out?
And then there's another prominent subcategory of supervised learning, which is classification. And classification means to group the output into classes. And I get hungry when I see this picture, but it is not necessarily a muffin that I see, right, Matthew?
Correct. So in typical classification, we start by training an algorithm, feeding it a series of photos. In this case, some of those are little dogs, and in some cases, muffins. And to start off with, the algorithm is being supervised. So we're telling the algorithm, this is a dog, this is a muffin. But over time, we allow then the algorithm to start taking decisions, and we correct it when it's wrong. And sort of the end goal is that the algorithm becomes very good at using its visual processing to determine whether we're looking at a dog or a muffin.
And then we've got the next category, which is unsupervised learning. In supervised learning, you uncover hidden patterns from unlabeled data rather than finding correlations between, let's say, X and Y. A very prominent example for unsupervised learning is anomaly detection. And an example for that would be that you might have a pool of data and would want to group that data into different categories. But due to the nature of your data, you might not know what these categories would be, or you might only know a few. So the aim would then be to run your machine learning algorithms to gain the knowledge from the masses of the data, which for you as a human being seem to be totally homogeneous. And this is known as clustering, the most famous branch of supervised learning. And then last but not least, we've got reinforcement learning. For that one, neuronal networks would be the buzzwords. But it's not always that easy, is it, Matthew?
No, certainly not. Machines are really good at looking at patterns and detecting correlations. So you see up here 4 great examples of what we call in the industry Spiralis correlations. So if we all think back to high school science, basic 101, association does not necessarily lead to causation. We get taught that as human beings, but the computer doesn't know that. So, you know, my favorite on the screen here is per capita consumption of mozzarella cheese correlates very strongly with civil engineering doctorates awarded in any given year. The human mind clicks in and says that that's an unlikely outcome. And of course, we can do some refinement testing to verify that. The other very classic example that I first heard when I started studying machine learning is an increase in drowning deaths is very strongly associated with an increase in ice cream sales. Now, the computer spits that out as a result, and the human mind needs to interact with those end products and look at it and say, well, obviously, the underlying common denominator in that equation is warm weather or abstractly summer. Alex, I think let's take them through then what a machine learning project looks like.
Wow, this is such a good idea. So let's start to understand that by contrasting how traditional programming works opposed to engineering a machine learning project. So in traditional programming, you've got your core program and then you fill it with input data. The computer then goes and validates the data and calculates a certain output. And this works perfectly well, and it creates a great value. It also creates a great value in our traditional projects for our customers. In machine learning, it works slightly different. We've got our data and we've got the results from, for example, our existing traditional software projects. And now the task for the computer is to calculate the relation, or let's say the context, between the data and the results. With that input, it then writes the program. So to put it into a nutshell, or to give it different words, machine learning is when the computer autonomously learns to derive decisions from data. And let's have a look about how a typical machine learning project could be set up, or how we could conduct it. As always in a project, we've got a number of milestones, and those milestones come with the time they consume. So we've got the rough indicator for the time they consume on the right part. When setting up a project, it is, as always, the first milestone to involve the right parties, your IT department, your operations, your management team. And then the first task is to define the result you actually want to achieve in the machine learning project. So then typically the data scientist sits down with the customers or the customer and then discuss what is the problem we want to tackle. Secondly, you have to gather the data. That can be very tricky, as there might be multiple sources of data, and you will have to pull them out of multiple databases or Excel sheets or any sources of data, and the data will mostly be not be in the format you will want to work with. So the data scientists will then have to do a lot of cleansing of that data. And then comes a very interesting part. Once you've got the data and once you've got it you've got it pure in the pure form you want to have it, the data scientists would do what is called feature engineering and convert the data into something an algorithm understands. And those are numbers. And that's the tricky part, which I intend to show you in a few examples later on. So when we take a look at the time indication for that part, we've already after that spent 80% or spent 90% of our machine learning project. And it's really important to put a lot of emphasis into that part. And for the rest of the time, it's finding the right mathematical model. This could be linear regression. This could be decision trees or random forests, just to mention a few. And the applied model would lead you to the 8 outcome: tuning the model, test the model, and re-evaluate the outcome. And then in the end, you measure the impact. So in the end, you will have identified certain pieces of data which are most important to achieving your previously determined goals. So that's the theory. Let's find a practical example.
Alex, as you well know, we wrote 2038, a Smartport story last year, and we finished that in November. Even my co-author, we've envisioned what the future of container terminal operations might look like in the year 2038, which was, of course, 20 years from the time we started writing the piece. We're sort of interested in turning it into a movie, and we're curious if we invest a certain quantity of money, whether we're going to see a return on that investment, because obviously it's not Inform's core business. Do you think we could apply machine learning to understanding and predicting whether that film will be a success?
Yeah, let's give it a try. So again, we've got our milestones, which I explained before, listed over here, and the first milestone would be defined what we actually want to achieve. So we want to find out whether our movie would be a success or not. And since Matthew wants to gain some pocket money, and since Matthew also wants to get some fame, we will measure the success by revenue and the rating the movie gets by the audience. Well, how are we going to do that? We are going to apply machine learning to predict the defined success based on the success of previous movies in the past. So in our machine learning project, the second step would be the 80% chunk, which I talked about before. So we have to start with data collection. In the example we're going to use during this webinar today, this is quite an easy task. So there is the database called TMBD database, and this is available for free, and it makes the data available via a very nice API. That means that all the data we are interested in is transmitted via this interface. This is a huge advantage compared to the most real-life data science projects, because we don't have to gather the data out of multiple sources and formats, but we rather receive the data in a nicely converted format. It also makes data cleansing easier, as we can easily pick the data fields which seem of importance for us. Just to mention a few, those are, in this example, the actors, the language, the duration of the movie, the country of success, the budget, the revenue, and so on. And now comes the tricky part, which is the feature engineering. As you remember, this is converting the data into a format that the algorithms can work with. Basically, it's converting data into numbers. And when we consider the budget and the revenue or the number of the ratings, it's easy. We've got numbers. But for other data sets, it's a bit trickier. Like if we want to convert, for example, language or the actors into numbers, the task for us would be, how can we quantify an actor or a language or even a movie title into numbers. So we go and illustrate that by an example. So to measure the impact of an actor in our movie, we have to convert the actor into a number. Please don't try this at home. To do that, we create a formula. We can take an actor and sum up all the movies the actor has played in, multiply the number of votes with the average rating of those movies, and then we get a certain outcome. And the result is as follows. With the data we got via the interface, we see that good old Leonardo DiCaprio is in the first place, followed by Tom Hanks and Robert Downey Jr. So it's quite a popular cast. And we may say that we've quantified the data we have into a measurement, which are numbers. It gives us the opportunity to see how good or bad the movies are, and if we enter data elements, so the actors, into our algorithms to learn about the success of the movie. So once we finish that one, once we've got this ticked off, we go to the next step, which is modeling and evaluation. Again, we take our data set and let it run through the regression model. Once this is done, it is hugely important to split the data into training sets and into test sets, because for the sake of quality, it can be dangerous to test an algorithm based on the data it has learned from. So what we did, or what we will do in this movie example, is we spread the data on a time axis and then define a split on that axis to use the data before the split as the training data that would corresponds to 75%, and then the latter part as the test data. And then we would come to the results. And the result is expressed in the mean average error. That's the abbreviation MAE you see here on the slides in the last column. So in this machine learning project we run, we found out that for the revenue, one can predict an average deviation of roughly $90 million. And for the rating, we would predict a deviation of roughly 0.6 rating scores. And to judge that proof of concept for the score, I guess, it would be a reliable value. But for the revenue, I think that your investors won't be too happy, Matt, since the risk of deviating by $90 million would be quite a big one. So just to dig into that, what we would do in a proper machine learning project, not just a proof of concept as we did it over here, is we would put more emphasis into the mathematical model to solve the problem, so that it would narrow down the MAE for the prediction of that gap we identified. So as a conclusion, we can say that the machine learning told us whether a movie would raise a revenue given our inputs and how the rating would be. And we learned that two things which would be there which would impact our measures for success, which are the revenue and the rating the most. For the revenue, or on the revenue side, it was quite important how big the budget is. The bigger the budget, the more successful the movie is. And the second criteria, and that was a criterion which surprised us a bit, is the popularity or the rating of the fourth actor in the cast. And that wasn't something which we really expected. And for the rating, so the influential factor for the rating would be the runtime of the movie. So how long is the movie? And again, the fourth actor in the cast. Are you convinced, Matt?
Well, like I said at the beginning of the webinar, Inform being privately held allows us to do things that maybe all public held companies aren't so free to do. And we actually built this machine learning algorithm and put it to the test. So let's look at what that looks like. I've gone to the board and I've asked for $80 million for budget to put together a 90-minute crime film released in the English language in the US on the 22nd of November, right around Thanksgiving, which before COVID-19 would probably have been a pretty good time to release a film. And we've put together a fairly decent cast there, from Benedict Cumberbatch, Meryl Streep, down to, quite importantly, Emily Blunt in our fourth actor position. Emily Blunt has quite a good rating. So we chucked that information into the algorithm as a set of variables, and its prediction was that we would make $44 million with a rating of 5.53. Now, I'm pretty happy to make $44 million for Inform, but I'm not really happy with a 5.53 rating. So we started tweaking the variables, of course, learning that if we increased our budget, we'd likely get to a higher revenue. We tried that, and we can see here in the second example that we increase our budget by 20 million, and that results in a significantly higher revenue, up to 77 million. But again, that rating hasn't moved. And on a third revision, if we increase the runtime to 180 minutes, so 3 hours, quite a long movie, but we suddenly see a 2-point jump in our rating. And interestingly, another sort of 70 million jump in our profitability. So runtime consequently probably has an impact in overall profitability. As Alex noted, looking at this fairly basic machine learning algorithm that we've put together as a proof of concept, it shows that there is some legs to what we've started, but there are certainly deeper questions, because at this point it didn't matter what I changed, I couldn't get the rating higher than a 7.3. So there's probably some other underlying associations, perhaps around the genre or the language or the country that it's released in, to determining the film's overall success. Now, fun aside, Alex, we've learned a little bit about what's involved in a machine learning project. Why don't you take us a bit through what we've actually done in container terminals?
So basically, also to wrap up what we've learned during this webinar is the question, how can we transform what we've learned into the world of container terminals? And to do that, I reiterate the definition of machine learning from the very beginning. Machine learning is that the computer autonomously learns to derive decisions from data. So you can wonderfully apply this when predicting crane execution times. When you do that, rather than making use of your base data, let's say, for example, acceleration and pick and drop off times, you can also learn about dwell times and the outbound transport mode of containers and how they help you to build nicer stacks in the yard and to, in consequence, have less re-handlers. And of course, predictive maintenance is an issue of interest. So for the last few minutes, let's focus on a project we've done in Germany, and we've gone live with them at the German maritime terminal. At this terminal, the Inform Yard Optimizer allocates the yard slots for every container in the automated yards. And of course, the overall aim of the Yard Optimizer is to minimize the re-handlers when stacking containers. So what we want to do is we want to actually check how did we do that. And that's the next slide. So what we see on this slide is a mosaic plot which shows the outbound transport mode, which was expected based on the TOS information, so the information as an input, versus how the container departure could actually be predicted by machine learning, or how it has been departed. So the areas represented are proportional to the volumes of containers which are handled. We see on that slide that there is a lot of gray color, meaning that, for example, when you take a look at the rail section on the left part, a majority of the outbound transport was unknown upon arrival of the containers per rail. You can also see in this picture that on that terminal that it's a maritime terminal, since most of the containers arrived and left by vessel. So as a next step in that project, we took a look at why that is. And based on our human expertise and our knowledge in that project, and based on actually knowing the input data for a decision on on allocating a container in the terminal, we identified 16 variables which we thought would influence the determination of the outbound transport mode the most. And then by using random forest, applying classification and regressing methods, we measured the importance of each variable. And we also detected an outcome of that one. And that outcome was what we see on this slide. And it basically flips what we saw on the slide showing a lot of gray. So we see that, in the mapping of the outbound transport mode predicted by the TOS versus the machine learning data, that we can see significant improvement when it comes to determining the transport mode of containers arriving by rail and feeder. Yeah, we could actually detect that we could help to solve the problems by machine learning. Yeah, we also did some more research on that terminal, which is concerned with the dwell times of containers in the terminal, since dwell time is a central variable in optimizing the placement of containers for the sake of minimizing rehandlers. In the example of our terminal in Germany, the data points to determine the dwell time of a container was the expected time of departure sent by the TOS. And in that case, it has frequently been missing upon container arrival at the terminal. So what we see in the slide is the outcome of an empirical model to determine the mean dwell time. That is by using historical data for those containers for which the dwell time has been unknown upon arrival. And again, in the next step, we wondered what would happen when we would factor the dwell time versus the expected departure mode. So we again went and identified the data elements which were the most important drivers for the determination of dwell times. This could be seen in this slide. Yeah, those were mainly the port of discharge, so the route of the container through the world, and the shipping line. But there were also timely factors like the month or the weekday. And it was interesting to detect that the data, which was provided by the TOS, so it was not only showing that the data was missing, but in some cases it appeared that the input data was wrong. We transferred those data elements, let's be more clear, into random forests with 500 iterations to train the algorithm, and the forest was tasked to identifying the importance of those variables.
I'm going to take over for a second. It's quite interesting that whilst we set out to look at improving the standard variable from that sort of just under 100 to something that's a bit more specific to each container, we found some very interesting things, which when we look at this decision tree looks like common sense. We see at the top that if we don't know anything about a container, the machine learning algorithm recommends roughly 83-hour standard dwell time. That's down from the 96 that the empirical model calculated. And if we take at a first cut port of discharge, which is information we hold for just about every single container in the TOS, regardless of whether we know when it's going, we definitely know where it's going. And we can do some simple country classifications. And in doing that, we can see if the container is going inland into the hinterland or if it's going out by deep sea vessel. And it gives us a fairly accurate estimate of whether it's a ship which has a longer time at port, a ship container that has a longer time at port in the yard, or a train or feeder barge or truck deport. From there, again, we see at a second level the outbound mode of transport has a very significant role to play, with a deviation of some 20 hours in the overall, where we know the outbound mode of transport versus when we don't. We move down another tier, we see the shipping company, and if we move down to the bottom tier, we were actually quite surprised to find that the weekday of arrival had a very significant impact on this particular port, because in fact it's a 24/7, 7-day operation port. But we sort of were able to isolate that on Saturday and Sunday. The truckers don't often come into the port. At least the frequency decreases quite substantially. So containers arriving on Friday or Saturday tend to dwell for an extra nearly 20 hours in port. Quite interestingly, it highlighted very clearly for us the association between dwell time and the outbound mode of transport.
Yes, this is exactly what our last slide shows, namely the dwell time per expected outcome departure mode. So in purple on this slide, you can see the containers leaving by vessels, that they stay longer at the terminal. So the bar in the middle of each rectangle represents the median, which then can be used as the indicator for the dwell time for the optimization run when determining a stacking position for the container. We also see that rail containers leave the terminal the quickest. Those are the red ones at the bottom. And it's also interesting, since we've got this nice mix of dwell time and outbound container mode, that for those containers where the transport mode is really unknown, so the gray ones on top, we can still calculate a more accurate dwell time and minimize the odds rehandler. So as a conclusion, when feeding this data or these insights as input into the yard optimizer, we achieve a significant reduction of rehandlers in the yard, since the input data is just smarter.
Alex, thank you very much for that detailed analysis. Hal, I think you're going to jump in.
Yeah, that was terrific, guys. I can't thank you enough. We've got some really interesting questions coming through from the audience. I'll start out with this one. Our organization is a few years away from automation. Would machine learning make sense as we consider automating certain parts of our operation down the road?
Yes, probably. So since I don't know the operations, it's not a question I can answer with a clear yes, but as I can judge from here, I seldomly see that a business is not really suited to do such projects. I mean, like in machine learning projects, it's the same as within the business. Machine learning projects can be small, as businesses can be small, and machine learning can be huge, as businesses can be huge. A nice indicator to find out whether you're suited or not would be that you ask yourself if you've got many data entries which are entered manually into legacy systems, for example. Because if you've got many manual data entries, you've also got a lot of sources for wrong data input. And if you put that into, let's say, for example, Excel, you sometimes find or you don't find the error within your data sets. And then data science and a machine learning project could help you to get clearer data.
Here's a good one. Under what circumstances do you not recommend using artificial intelligence and machine learning models?
The simple answer there is if you are very early on in your digitization process. Machine learning, as I noted when we sort of looked at the high-level artificial intelligence, is dependent on data. That's the topic of this presentation in this webinar. Where you don't have access to data because you're early on in that digitization process, it becomes kind of a cart and horse conversation. In those cases, it's generally worth getting more of your digitization into order. For most terminal operations, the general rule of thumb is if you're running a TOS and you've been running it for 6 to 12 months, you have enough data in general for us to start, or for anyone doing data science or machine learning project to start gleaning insights. Those algorithms will only improve over time, but again, that fundamental starting point is data.
Yeah, and it sounds like the subtext there is that I think a lot of us probably have more data than we think we do. So here's a good question, sort of a nuts and bolts one. Who typically drives a machine learning project within an organization?
So I would say basically as always, the ones who want to improve the business and the ones who make the strategic decisions. So mostly management, since they want to squeeze out the most of their business. But also, as stated before, it's a task of the organization of to define what they want to achieve. And to do that, you would have to get a rough picture about the data you have in order to achieve that. And sometimes there is a fear that you don't have enough data. Sometimes the fear that you can't really pull that data out of your sources, that you can't convert it. And this is when the experts come in. What I would also really want to stress is, and that might be my personal opinion, is to involve the operation girls and boys into that process, because those are the ones who know the reasons for data being connected to each other, and they know the causes for the outliers. We, as the data scientists, but also as the ones who know the business, detect. So they are very helpful in also determining the goal of the machine learning project or the data science project.
And I would second that. The human expert in our machine learning projects is ultimately the most crucial point. So we've got data scientists, but we also pair them when we run a project with terminal operations experts, people who can interpret those results and say that's a real correlation that leads to causation and not just a happy coincidence.
That makes really good sense. And this one actually dovetails in nicely because, again, it's sort of taking it from the neophyte side. Do we need someone inside our internal team who's a specialist in data science or machine learning to run a project like the one that you've talked about?
Not really. There are a lot of larger ports that we're seeing investing heavily in data scientists, bringing them into their teams. But certainly that's not a trend that we're seeing in smaller ports, and it's not a trend we're seeing in our intermodal customers. What we're more seeing is leaning on an external service provider who has expertise in data science and experience in running those projects, who can provide those services in a low risk, potentially high reward scenario.
May I add something?
Yeah, please.
And what is also really important is when you remember the 80% chunk in the webinar at the beginning. So pulling the data out of your database to clean it and then to do the feature engineering. Sometimes or often this is a part where a data scientist who doesn't know the operations or doesn't know the business, doesn't know the domain, so who doesn't have the domain knowledge, can't really help you. So it's the teamwork between the customer and the data scientist partners, and to get it done. And the data engineering, so the mathematical part in the middle, is a quite small one. And even if you do that in a proof of concept, you can still get a very good outcome if the 80% chunk is done nicely.
What I'm hearing is trust your intuition, trust your ops people, because they know your business. Here's an interesting one. It's a little sort of chicken and egg quandary. The project outline that you presented starts by defining the project as a machine learning task. But how do we know if what we want to achieve can be done through machine learning tasks?
I think the easiest answer would be to say that you can find that out by talking to us. So in general, we never do projects without doing workshops and to finding out where the bottlenecks are or how we could help. So if we would talk to you, you would explain the problems to us and you would explain your business to us. We would find out whether probably a traditional business intelligence software project would be enough to solve your problem, or if you really need machine learning. So you could scale that one, and you could scale the complexity of the problem. So I think just talking and discussing makes everybody or each party smarter and helps both parties.
Makes good sense. Here's a good one. What are the risks to running a machine learning project?
We try really hard to mitigate risk through our projects. As Alex noted, the first step for anyone is sitting down and sort of saying, okay, we want to achieve something, we want to solve a challenge that we have in front of us. As a sort of first step, we offer an obligation-free consultation to understand if it's a machine learning project or not, and if we can actually assist. We have this, inner German in us that's bluntly honest at times, and if we can't help on a project, we certainly put that forward. But as well, the projects are designed in a way to mitigate risk, and I'll let Alex tackle that side of it.
So yeah, one means of mitigating the risk would be to do a proof of concept. So to really do the data gathering, the data cleansing, the feature engineering, and then to probably let an open source algorithm solve the problem, and then to measure how much did we already gain. And this can also be a convincing part for the customer. So in our movie example, we saw that with that quick and dirty example we set up there in a few days for the webinar, and we already saw that we could make a huge impact by squeezing the data. So if we would go and putting more emphasis on the solvers, then we could achieve a better data. And another means of mitigating the risk is to, of course, never directly take it into production, but let it run parallel to production to compare results and to see the actual measure or the actual impact it would have when it would be connected to all the inputs interfaces, and not switch it off switch it on directly.
Yeah, no, it makes sense. I think we can sneak in maybe one more question here. This one sounds like one of my motor carriers. I run a small business, and I don't think that I'm digital enough for such a project. Is that right? Would you guys agree with that?
I think it comes close to the first question you asked. So, as I said before, we seldom see that someone is really not suited to do such projects, as you can scale them, and you could also do small business intelligence projects, and there are some indicators which can help you to find that out. So how much of your business decisions rely on the system's base data? So if they heavily rely on the base data, and if you as the manager or the operations guy tend to find out that base data is not only correct or it has holes like a Swiss cheese, you can call the Germans.
The only thing that I'll add to that, Hal, because I like having the last word, sorry, Alex, is data is everywhere. We live in a very digitized world, and it's surprising often where data is hiding. It could be that the first step is not a machine learning project, but in fact something to get your data in order, and to better categorize and silo that data into a more organized structure. And there's certainly room for any operation to tackle projects like that.
Got it. Okay, I'm going to lie and actually ask one more question, because I like this one. The questioner asks, I hear that you use quite a simple machine learning model like random forest and decision trees or linear regression classification. My question, are these models good enough for a container terminal, or do we need more complex techniques like boosting or stacking?
Yeah, the biggest chunk is done at the beginning. So for the two specific examples we used in here, we presented in here, we used random forests, but it's not the end of the road. So we're continuously improving, and we already saw that based on that, what we actually did with those or as the one who asked the question said, simple methods, we see that there is a huge outcome, and the huge outcome is to predict better dwell times and to predict a better outbound transport modes, and to make nicer stacks in the yard, and to minimize rehandlers. And rehandlers are a measure for costs for container terminals. So if you can even reduce them by a low percentage, the monetary outcome for a terminal would be quite huge.
And I will only add, not to have the last word, but to only add that in container terminal operations, both in maritime and in intermodal, machine learning is very much, it's still in its infancy. We're starting to see ports and terminal operators show interest in it. And so far as we can generate quite significant benefits, and I can say that we're generating quite significant benefits for our customers using the more simple techniques, we'll continue to do that. Once we've sort of milked those simpler models for the sort of results we can get from them, then of course we move on to sort of more complicated algorithms and modeling processes.
Right, no, that makes sense. Well, folks, that was really super interesting. I mean, I really appreciate you taking the time to kind of walk us through that and get us set up. I'd like to thank all of our attendees for spending time with us today. I would like to take this opportunity to, again, thank our sponsor, BlackBerry Radar, for their support. It's been great. If you're looking for more information about IANA in general, about our webinars or our programs, our committees, feel free to head over to intermodal.org or just go ahead and email us at info@intermodal.org. And with that, I would like to thank everybody for their time. I really appreciate it. And everybody stay safe and stay sound, and we will see you next time.